Bonjour à tous. Welcome everyone. Gives me great pleasure to talk this morning here. Comme Sarah le disait, c'est un moment important pour réfléchir aux risques de l'intelligence artificielle et l'importance de réglementer. I think the progress we've seen in the last few months really raised a lot of questions and I think prompt us to accelerate the pace at which governments need to protect all of us with technology, which could be amazingly useful and also risky. Aujourd'hui, je vais vous parler de ce qu'on pourrait améliorer de l'IA actuelle pour qu'elle soit plus fiable et robuste. One of the things that I'm thinking a lot about is how can we build AI systems that go beyond some of the limitations, especially in terms of reliability and truthfulness of the systems that we currently have. So, I'm very impressed by ChatGPT and the GPT-4. It's something that came much faster than many of us expected, but it's lacking major elements from a machine learning point of view if we compare with humans. And this is what my talk is going to be about, and some directions to try to fill that gap. So essentially, it's about reasoning and reasoning the way humans do it. In particular, one aspect of reasoning that I think is quite important for humans and that is completely missing in current systems is causal reasoning, which includes the ability to explain in similar ways that humans do why the system is taking decisions. Now, humans are not perfect at that by far, but that kind of high-level ability to connect cause and effect and explanations is something that's clearly missing. Finally, from a more machine learning perspective, the biggest challenge with the current approaches is they need huge amounts of data, like 10,000 times more than a person would be reading every day for all their life, and still make generalization mistakes, which we call out of distribution, meaning if you ask them questions that are somewhat outside of the kinds of data they've seen, where they're failing in ways that humans seem much more robust. So what is reasoning? In machine learning, we use this term inference or probabilistic inference, meaning given the knowledge that we have, what is coherent with that in order to answer questions? And the way humans reason is that something different from what we see in the current large neural nets. What humans do is compose pieces of knowledge, select pieces of knowledge and combine them in coherent ways in order to come up with answers or explanations or imagine future things and plan. And one of the major sources of inspiration for me thinking about how we can improve current AI and make it safer comes from decades of research in neuroscience and cognitive science about how we think. And there's a famous theory of conscious processing called the global workspace theory, which has been inspiring a lot of my work. So the hypothesis that my group is working on is that a lot of the weaknesses and gaps and failure modes that I've talked about for current AI systems can pretty much be boiled down to the fact that the current systems we have are missing something fundamental in human intelligence, which is our conscious processing. And I'll dig a bit more into this. So when you are faced with something really novel, for example, let's say you've been driving in North America all your life and then you rent a car in Australia or in London where you have to drive on the left rather than the right. A lot of the way you should be driving is going to be different, and yet we adapt very quickly to that. Now, if we pay attention to that process, when you are in this novel and maybe even dangerous situation, what's going on. You're paying attention to the current situation. You're thinking about what you're going to be doing. You're imagining what could happen because you have this new rule, just one little bit of information that has changed. Drive on the left rather than the right. And you're programming yourself so that your habitual behavior of driving is going to be modified. So all of these things are features that are present in human cognition that are not yet in AI systems, and they help us deal with new problems, deal with situations that are unlike, but maybe at an abstract level, not so different from what we know, like the example of driving, where everything is the same except this one rule has changed. Okay, so this whole discussion is connected to something I've been talking about for many years, which is being studied by cognitive scientists and neuroscientists, that there seem to be two different kinds of information processing in the brain, the system 1 and system 2. So roughly speaking, system 1 is everything intuitive, and system 2 is everything conscious. And the current deep learning systems are really good at the system 1 type of processing, very fast and habitual, and the knowledge that is being manipulated there is hard to extract. It's hard to ask the machine to explain what they're doing, and that's really what's going on in, a large part of what's going on in our brain. But we also have this system 2 abilities that are connected to things that we can verbalize with language, and that allow us to do things like imagine and reason and manipulate pieces of information, as I said, that we can then communicate with others. So how is that going to help us to generalize to new situations, so-called out-of-distribution generalization? Well, there is a fundamental assumption in machine learning which we need to revise. The assumption that all of the examples are coming from the same distribution. In fact, in real life, like the driving example, things change. You end up in a new place, and you have to very quickly change the way you're going to be behaving or interpreting things. And again, there is an inspiration from human cognition that may help us figure out how we could bring that power to AI systems. And it's the idea of causality that I mentioned at the beginning. It's also the way that science is trying to understand how the world works. So instead of modeling the distribution of the data as sort of one homogeneous thing, we think of it like a set of mechanisms, like the laws of physics. But the same mechanisms, same causal structure in different circumstances can yield to very different things. So the image with the Earth here is to say that even though it's the same laws of physics on the moon, the pictures would look very different. And if we can build AI systems that understand better how the world works, they would have these abilities. They would build a world model that is causal and that can then be applied to very different circumstances. So now this is a little bit more technical. If we want to understand causality, we have to refer to this notion that people in that field have called intervention. So the idea is when I do something in the world, it's like changing the initial conditions in my previous slide. It might be just a little change in one of the variables, like the constant of gravity on the moon. But the effect of this could be drastic. And so these interventions are something that we need to incorporate in our machine learning models. And really, we have these two kinds of variables that we should be modeling. We have like the ordinary variables, the ones that we observe or that we think about. But then we also have these interventions, like somebody did something, and that's changing the situation. Now, why this is powerful is that if we are able to learn good causal models, then we can generalize to new distributions corresponding to new interventions. So maybe I've never been in this new place and where driving laws are different, but there's this intervention. Somebody changed the law or whatever, and somehow I can predict what the outcome would be. I can simulate in my mind, well, now people are driving on the left, so that person is going to be turning this way and that way. I need to be careful about that. So one way to think about this from a machine learning point of view is that the idea of causality can be translated into constraints, what we call inductive biases. In other words, instead of just being completely agnostic about how things are in the world, we can take advantage of the same kind of knowledge that evolution has put in us about causality and wire that in our models, which is not something that we know how to do yet. Okay, now, so I've talked a lot about causality, and it's a very important part of my research. Now I'm going to tell you about something else which is kind of challenging for AI, but I think is important to build safe systems. So this is Bayesian learning. So what is that about? Let me explain in simple terms. When you observe data, or when a machine observes data, there may be multiple models, multiple causal models, multiple theories that are compatible with that data. And the usual way that we're training these large neural nets is we just find one model that fits well the data. That's like the regular, called maximum likelihood training. But that's not the way humans do it, actually. Somehow, there's a lot of cognitive psychology experiments that suggest strongly that humans somehow, at an unconscious level, entertain many theories that explain what they're observing, and then they act accordingly. So, for example, you can make bets that reflect the right Bayesian probabilities that come about because there are multiple interpretations of what we're observing. So being Bayesian here means exactly that somehow the learning system implicitly entertains the many explanations, the many interpretations that are compatible with the data, the many theories that are compatible with the data. We introduced a new machine learning framework that is aiming at tackling these challenges. The first paper on that was presented at NeurIPS 21. So this is a bit more than a year ago. And what this new framework does is making it possible to train generative neural nets, in other words, that invent stuff, but instead of inventing images or generating images or texts, they generate things that are more like our thoughts. And so they sequentially construct potentially symbolic or potentially continuous representations that maybe you can think of like your inner voice. And mathematically, the way this policy of generating thoughts is trained is so that it samples these thoughts with probability proportional to some reward function. And so this whole framework is directly connected to reinforcement learning, but also to generative models. And you can use let me skip that. You can use this to learn Bayesian probabilities that I was talking about before. So the way this works in kind of a simple example is if you want to use this to generate a data structure like a graph, is that the neural net will sample one little piece, like one piece of knowledge that's added to the pieces you have already selected. So in the case of a graph here, in the figure we see, we already have this graph with 3 nodes, 1, 2, 3, and then the neural net is going to stochastically sample a new piece, which here is the edge from 2 to 4, for example. So that sequential processing is very much like what we have in system 2 computing in the brain that I was talking about initially. Okay. What we've found a few months later after this first paper is that this whole approach is closely connected to a tradition in machine learning called variational inference. But it actually helps to deal with some of the limitations of those previous approaches. Now, what is important here with these variational approaches and those G-flow nets, new method I talked about, is that they allow to take knowledge of the world, which might be represented by some piece of network, and convert it into an inference machine, something that can answer questions, so that we can have basically the system 1 part that's going to be able to take decisions, answer questions very quickly, while when it's being trained, it decomposes things in many possible ways, which is like system 2 thinking. What we've done also more recently in the last couple of months is introduce extensions of this theory so that it can handle not only the discrete symbolic objects, but also continuous quantities, which of course is very important in machine learning. For example, if we want to be Bayesian about parameters of a model, then we want to have tools like this. Now, let me say a few words about another application of this framework, which goes back to my initial discussion on causality. So one of the big questions in causality is, and something psychologists also ask about how humans do it, is how do we discover the causal structure? So let's say if you have multiple variables that you observe, and you want to know which one is cause of which one. And that forms a graph. So here you have these 3 variables, A, B, C. And people have been focusing in the past on trying to find one graph that fits the data. That's the maximum likelihood approach, if you want. With the approach that we've been developing with these G-flow nets, the neural net will generate candidate graphs and will be trained to sample graphs from the Bayesian posterior, because there's a lot of theory and evidence that given any finite amount of data, there are a lot of possible causal explanations. In other words, possible causal graphs. It could be that the graph has, follows one of the graphs you see in the figure, or another one with different probabilities. And the right thing to do is to actually represent all of them, which seem intractable, but actually can be done if you do it implicitly, which is exactly what this does. And so the system would, at any moment, only generate one theory, one hypothesis, one causal graph, but really it can, while doing so, train a decision-making system that takes into account all of the possible graphs that can be sampled from that distribution, and that's very much a mirror of what we see in human behavior. So the paper was presented last August at the UAI conference, and it's called Bayesian Structure Learning with Generative Flow Networks. The last thing I want to mention goes back to the initial discussion about ChatGPT and large language models and what's missing in them. So one problem with these approaches, and again, a difference between the way humans do it, is that they directly learn to fit the data, to answer the questions, to complete the text. Whereas it looks like humans and also scientists break this problem in 2 parts. One is what people call a world model. In other words, like the causal structure that I was talking about. How does the world work? What are the rules that explain things in the world? and the inference machinery, which is able to answer questions. These are two different processes. In current approaches, they're mixed together, and that leads to problems of overfitting and not generalizing properly. So what we think is that the approach that we are proposing allows to do that separation and eventually build AI systems that are more like scientists, that build theories of the world, and then, if you want, like how to build bridges with that theory. Okay, so there's a tutorial online about GFLNS if you want to learn more. And je vous remercie beaucoup. J'espère que ces directions de recherche vous ont intéressé. Et I want to again tell you that it's important for the scientific community, but also for the society at large, to start thinking about how we want AI systems to be used. Qu'est-ce qu'on veut faire de cette technologie? Il faut absolument que ce soit centré sur l'humain, sur nos besoins, sur nos valeurs. Merci.
Thank you very much, Joshua, for that talk. And I think we have some time now for some questions, if you're happy to take some. So please raise your hand if you have a question. I'm sure we've got plenty. There's a gentleman here in the middle section, and we will send a microphone over to you. There's one running right now. Thank you for your athleticism.
Thank you very much, Professor. I'm a business professor and a business ethicist. Seems like we have a real dilemma. We in the university are, of course, the leading edge of AI technology, and we are pushing the agenda. However, for-profit, investor-driven organizations are actually implementing and rolling out AI systems. What do we do to mitigate that negative impact of the for-profit driven world against the need for ethics and safety?
This is a great question. Thank you very much for asking it. This is something I've been thinking a lot about in the last few years, and especially in the last few months because of the acceleration of AI. And in the short term, there's a very simple answer. Governments need to put in regulation, okay? And they need to accelerate the rhythm because parliaments in democracies take a lot of time to get laws passed. So one of the things I've been pushing is for legal frameworks that are going to be agile and adaptive because technology is moving so fast, right? So we need principles-based laws that can then support regulation that can change as new risks appear, new nefarious uses of AI show up, and we need to quickly protect the public.
Thank you, Joshua. Dynamic legislation. We have a question here. I'm trying to look at where are our mics? So we have one here, and I can see two over there. Oh, microphone. The lady here, raise her hand again. Thank you. We'll go over there next.
Hi.
It works.
Yes, on.
Oh, okay. Hi, I'm Pam Kamath. I work in the risk management. I've been focusing a lot on AI trust. My question is, as we know, regulations are always behind. And you said adaptive in nature, which is something I don't often see, as with the GDPR. We're yet to see the second revision of that. And I have a number of scenarios that I can say that are not GDPR compatible. Just going with that example, and also India is refusing to implement a regulation. The US is behind. We always need to have a plan B. Do you have any thoughts on that? Because nothing like saying, you know what, here's the best case scenario, here's the worst case scenario. What's the plan B? Do we?
We have to be creative. I think, one thing I like is the idea that's been circulating by researchers like Gillian Hadford, that we need innovation to take place not only in the technology, but also in the regulatory process. And she has ideas about how to do that. But I agree, it's kind of very concerning that the way our society currently operates is too slow to adapt to technological changes. One thing that can make that process faster is public opinion. So, if you talk to politicians, the thing that really drives them is when a lot of people think they have to do something. So hopefully, the discussions we're having like today and elsewhere, and the letters that I've been involved in, will help not only directly sort of stimulate governments, but we need the general population to start putting that in their political agenda so that governments take it seriously.
Thank you for that answer. And I think we have, let's squeeze a couple more in. There are some hands. Raise your hands high so our microphone runners can see you. I think there's someone maybe 3 rows back in this section here. Yeah, I think you see, yeah, here we go. If you stand up, there we go. I think there's a microphone coming your way. Please say who you are if you like and ask your question.
Hello.
Vous pouvez poser vos questions en français aussi.
Okay. Thank you very much for the talk. I was wondering if there could possibly be not alien-like, but non-human-like reasoning capabilities or systems that could be either more efficient or could bring us to similar capabilities than human-like reasoning.
Thanks for the question. So first of all, the scientific consensus is that our brain is a big, complicated, stochastic machine. And so we will probably figure it out. And there's no reason to believe we wouldn't be able to build machines that have similar capabilities. Once we understand the principles, and we've made a lot of progress on that, so it's like birds and airplanes. We don't have to build machines that have exactly the same structure as our brain. Maybe there are better ways of doing things. In addition, we may choose to develop AI systems that are actually different from humans, for example, so that they'll be safer and that we don't mix them for humans, because humans tend to anthropomorphize, and that could actually be pretty bad. So there are a lot of choices, collective choices, that we'll have to make in the coming years and decades. It's a great question.
And I'm sorry, unfortunately, I've been told that has to be the last question, but please put your hands together for Yoshua Bengio. Thank you very much. Thank you. Just a quick note, for those of you who are stood in the back, there are a good sort of 10, 12 seats down here. If you want to rest your legs, don't be shy. Just to the, I guess, my far left, there are plenty in the front row, so do feel free to filter down. Don't be shy. Wow, now on to the next. After that fascinating talk by Yoshua Bengio, which I hope you enjoyed very much, we are continuing the conversation, and we're going to have Sherry Marcus, who is the Director of Applied Science, Artificial Intelligence and Machine Learning at Amazon Web Services. Sherry was a founding member of the Science Board at the National Counterterrorism Center and is an advisory member at the Allen Institute. She received the Technical Medal of Excellence from the Central Intelligence Agency, which I don't think many people can say. And she's here today to talk to us about accelerating AI and machine learning innovation from theory to practice. So please put your hands together and give a warm welcome to Sherry Marcus.